All right, let's dive into one of the most fundamental ideas in all of physics, the electric field. This is the invisible force that runs pretty much everything, from that little static shock you get from a doorknob to the light that's literally hitting your eyes right now. It's like an invisible architecture that shapes our world, and today we're going to map it out.
But first, think about this for a second. How do things actually feel a force without ever touching? You pull a sweater over your head and your hair stands on end. Or two magnets push each other apart when they're not even making contact. It's this whole mystery of action at a distance. How does one object even know the other one is there? Well, the answer to that question completely changed how we see the universe.
And the answer is the electric field. Just imagine that every single charged object in the universe creates this invisible web all around it. It's like a force map that fills the space. And any other charge that wanders into this map instantly knows which way to go and exactly how hard it's going to get pushed or pulled. It's the way the universe sends messages about force across totally empty space.
So, here's our game plan for today. We're going to start with the absolute basics, what an electric field even is. Then we'll look at the simplest building block of all fields, the point charge. From there, we'll build up to more complex shapes, explore the kind of weird rules about what happens inside versus outside a charged object, then we'll put it all to the test with a real problem. And finally, we'll zoom out and see just how big this idea really is.
Okay, first up, what is an electric field, really? Let's lock in the core definition, because once you get this, everything else will just click into place. So here it is, the heart of the matter. The electric field, which we call E, is just defined as the amount of force, F, that one unit of charge, Q, would feel at any given point. So the formula is simple. E equals F divided by Q. And we measure it in newtons per coulomb. A newton is a unit of force, and a coulomb is our unit for charge. So this isn't some vague idea. It's a super precise measurement of how strong that push or pull is at any spot in space.
Now, the direction of that force is absolutely crucial. By convention, scientists decided that the arrows on our force map always point in the direction a positive charge would get pushed. So you drop a positive charge into a field and bam, it goes right along with the arrows. But, and this is key, if you put a negative charge in there, like an electron, it gets shoved in the exact opposite direction. A super simple rule, but you have to remember it.
Right, so to understand the fields from all these big, complicated objects, we have to start with the most basic case there is, the field from one single solitary point charge.
And this is it. It's actually beautiful, right? For a positive charge, the field lines just radiate straight out in all directions, kind of like rays from the sun. For a negative charge, they all point straight in. And the strength of this field follows a really simple rule. E equals K times Q divided by R squared. Now that R squared part is super important. It means the field gets weaker really fast the further you get from the charge. We call that an inverse square law.
Okay, so we have our fundamental building block, the point charge. Now we can start putting them together to build some more interesting stuff. Let's see what happens when we arrange these charges into different shapes.
Okay, check out this charged ring. The formula there looks a little complicated, but it just tells you how the field strength, E, depends on the ring's total charge, Q, its radius, A, and how far you are from the center, X. But here's the cool part. Look what happens right at the very center of the ring, where X is 0. The whole formula goes to 0. Right in the middle, the electric field vanishes. Why? Because you're being pulled equally in every direction at once, and it all just cancels out.
And this graph tells that whole story visually. You start at the center where the field is 0. But as you move away, the field actually gets stronger for a little bit. It hits this maximum peak strength, and then it starts to get weaker and weaker, eventually fading away to nothing as you get really far away. It's a little weird, right? But it's a perfect picture of how all those forces add up in space.
So what about a super long wire? For a wire, the field points straight away from it, everywhere along its length. And here, it's not so useful to talk about the total charge, because the wire is infinite. Instead, we talk about its linear charge density. That's the Greek letter lambda, which is just how much charge is packed into every meter of the wire. And fun fact, unlike a point charge, the field from a long wire weakens more slowly. It's proportional to 1 over r, not 1 over r squared. Now, let's look at a flat sheet of charge. It really matters whether it's an insulator, a non-conductor, or a conductor. The important variable here is sigma, which is the surface charge density, basically how much charge is spread over a certain area. On an insulating sheet, the charge is just stuck on one side. But on a conductor, those charges are free to move, so they spread out over both surfaces of the sheet.
And what does that do? It literally doubles the strength of the electric field coming off of it. It's a small detail, but it makes a huge difference.
Okay, this brings us to a really fascinating, kind of mind-bending idea. When it comes to electric fields, your location is everything. The rules can be completely different depending on whether you're inside a charged object or outside of it. This right here is one of the most incredible results in all of physics. If you have a hollow sphere made of a conductor and you put charge on it, the electric field, anywhere, inside that sphere is exactly precisely zero. It's not just weak, it's zero. The pull and push from every single charge on that surface perfectly cancels out. But the second you step outside that sphere, its field acts exactly as if all of its charge was crushed down into one tiny little point right at the center.
But what if the sphere isn't hollow? What if it's a solid ball of insulating material, with charge spread all the way through it? Well, on the outside, it's the same old story. It still acts just like a point charge. But on the inside, things are totally different. The field is actually zero right at the very center, and then it gets stronger and stronger in a perfectly straight, linear way as you move out toward the surface.
And this graph just sums it all up perfectly. On the inside, you see that straight line, linear increase of the field strength as you go from the center out to the surface at radius A. That's where it hits its maximum strength. Then, the instant you cross that surface and go outside, the field starts to drop off, with that classic inverse square law just like a point charge.
So, you might be thinking, what's the point of all this theory? Well, let's put it into practice. It's one thing to know the formulas, but it's another thing entirely to see how they can actually predict how things move in the real world.
So, let's take a look at this problem. We've got a little toy car that has some electric charge, and it's on a surface with no friction. For 1 second, a uniform electric field pushes it, and it speeds up from a dead stop to 6 meters per second. Then, in an instant, the field completely reverses direction. So the question is, what is the car's average speed over the entire 3-second trip? So our plan of attack is pretty straightforward. First, we'll use that first second of motion to figure out the car's acceleration, which tells us how strong the electric force is. Once we know that, we can figure out exactly what happens when that same force suddenly starts pushing the other way for the next 2 seconds. We'll just track the whole journey, find the total distance it traveled, and then we can calculate the average speed. It's the perfect way to connect electric fields to the motion we can actually see.
And this table here really summarizes a powerful idea. Just look at the outside column. A point charge, a hollow sphere, and a solid sphere. From the outside, you can't tell them apart. They all create the exact same electric field, like their charge is all at the center. The real story, the interesting physics, only happens when you look at what's going on the inside.
All right, for our last section, let's zoom all the way out and see how this one concept, the electric field, fits into the grand scheme of things.
You see, this idea of a field isn't just about electricity. This whole concept of an invisible influence filling up all of space has become one of the most powerful tools in all of science. Even Einstein said that this was a huge leap forward from just thinking about objects pushing and pulling on each other. The field gives the force a home. It's a real thing that exists in the space between objects.
And that leaves us with one final big question to think about. We've seen that electric charges create an electric field. So, what about the other forces we know that act at a distance? Is it possible that big objects with mass create a gravitational field, and that magnets create a magnetic field? Well, that question right there opens the door to understanding pretty much all the fundamental forces that run our entire universe.